Imagine the ground beneath the American heartland churning with a violence that felt like the end of days. In 1811, a sequence of cataclysmic earthquakes struck the New Madrid region, so powerful they reportedly made the Mississippi River flow backward. By blending historical eyewitness accounts of sulfurous brimstone with modern seismic data, we can uncover the terrifying reality of these events. Today, we'll explore the fascinating intersection of science and history buried deep within our nation's core.
Imagine a continent on the brink of profound change. In the deep woods, Shawnee leader Tecumseh is tirelessly forging a pan-Indian alliance to resist American expansion. This struggle unfolds across the perilous Mississippi Valley, a wild borderland shared by trappers, pirates, and native settlements. But a new era is steaming around the bend. The departure of the New Orleans heralds the Steam Age, carrying the Industrial Revolution directly into the heart of the untamed wilderness.
Imagine the sheer panic of living through the winter of 1811. It began in the dead of night on December 16th, when a massive magnitude 7.5 earthquake shattered the silence of the Mississippi Valley. But the terror didn't stop there. Over the next 3 months, the Earth refused to settle. After a second major shock in January, the devastating hard shock of February leveled New Madrid and was powerful enough to physically reshape the course of the Mississippi River itself. To grasp our current risk, we must look back at the 1811-1812 sequence, an epical release of tectonic strain. These three massive events reshaped the landscape, forcing the Mississippi River backward and filling the air with sulfurous vapor. The scale was staggering, felt across 5 million square kilometers. It even rattled furniture in the White House. While sparse populations limited fatalities then, this history remains a sobering baseline for the raw geological power we are assessing today. Between December 1811 and February 1812, 3 massive shocks shattered the American mid-continent, each reaching magnitudes around 7.5. Because seismic waves travel so efficiently through our cold, dense crust, the felt area was 10 times larger than the 1906 San Francisco earthquake. The sheer power of this sequence actually reversed the flow of the Mississippi River, created Reelfoot Lake in Tennessee, and triggered vast liquefaction fields, leaving a permanent, dramatic mark on our nation's landscape. The 1811 New Madrid earthquake left a staggering footprint, covering 5 million square kilometers, 10 times the area of the 1906 San Francisco quake. Its impact was so vast that President James Madison felt the White House quiver 900 miles away, while church bells spontaneously rang in Boston. This incredible range is possible because the central U.S. sits on cold, unbroken bedrock, which acts like a conductor, allowing seismic energy to travel much more efficiently than across fractured plate boundaries. While we often associate massive earthquakes with California, the continental interior tells a far more startling story. Despite a lower magnitude than San Francisco's 1906 quake, the New Madrid events shook 5 million square kilometers, an area over 300 times larger. Because the stable rock of the Midwest conducts seismic waves so efficiently, these tremors didn't just rattle the region, they actually rang church bells in Boston and woke President Madison in the White House. We often think of seismic danger as a West Coast problem, but right in America's heartland lies a sleeping giant, the New Madrid seismic zone. This fault is very much alive, averaging over 200 microquakes annually. History reveals a haunting pattern of massive ruptures every 5 centuries, and we are now well within that window, with nearly a 50% chance of a major quake hitting in our lifetime. The question isn't if it happens, but when. The New Madrid seismic zone remains a massive threat, capable of magnitude 8 events that traditional models often fail to anticipate. Our research highlights a critical trigger. The 2025 Kamchatka anomaly validates celestial predictive models that isolate February 2026 as a high probability window for a major rupture. Should an 1811-style sequence repeat today, the results would be catastrophic, triggering the costliest economic disaster in U.S. history and widespread utility failures across 8 vulnerable states. The New Madrid seismic zone is powered by an engine, an ancient 150-mile rift system under massive tectonic pressure. But the real danger is the amplifier. Thick layers of soft alluvial soil sit atop the bedrock, intensifying seismic waves 5 to 6 times more than solid rock. It's like shaking a bowl of soupy sand instead of rocks. This extreme amplification is what triggers devastating soil liquefaction, effectively turns stable ground into a fluid, shifting hazard.
We've reached a critical inflection point where geological tension meets celestial alignment. For over 2 centuries, the New Madrid Fault has acted as a loaded gun, silently accumulating massive crustal strain since the 1812 sequence. This seismic amber is now at its peak. Our synthesis suggests the February 2026 Saturn-Neptune conjunction could be the final trigger, potentially sparking a magnitude 7.7 plus earthquake sequence, a powerful echo of history colliding head-on with our modern, vulnerable infrastructure. When we compare the historic 1811 baseline to our 2026 projections, the shift in risk profile is absolutely staggering. We're moving from a sparsely populated frontier of log cabins to a dense urban landscape of millions across hubs like St. Louis and Memphis. While our ancestors had zero warning, modern vector modeling now pinpoints a critical window for next spring. This isn't just about structural hazards. We're facing the highest potential economic loss in U.S. history.
When a major event hits the New Madrid seismic zone, we face 2 devastating physical realities. First, alluvial liquefaction will cause the ground across 3 states to instantly transition to liquid, triggering massive sand blows and compromising critical bridge foundations. Simultaneously, we'll see widespread subterranean severing. Modeling projects a staggering utility crisis. In Memphis alone, over 20,000 water and gas pipelines would likely rupture, effectively paralyzing the region's infrastructure and making immediate recovery efforts an immense logistical challenge. When we examine the New Madrid seismic zone, the immediate system shock on day 1 is staggering. In Missouri, over 2 million households lose power instantly, though recovery efforts successfully restore service within 90 days. However, the true weight of this disaster falls on Tennessee, which faces the highest level of absolute damage. With over 250,000 buildings destroyed and 60,000 casualties, we are looking at a displacement crisis affecting 260,000 people simultaneously. When we examine the projected economic impact of a major New Madrid event, the figures are frankly staggering. We're looking at over $56 billion in direct losses for Tennessee alone, with tens of billions more hitting Kentucky, Missouri, and Illinois. Crucially, these numbers only represent the immediate physical damage. Once we factor in the indirect multiplier, cascading supply chain failures and business interruptions, the total cost will likely double, creating the most expensive natural disaster in American history.
We've moved beyond theoretical models into a period of imminent risk. The Kamchatka anomaly proved megathrusts can rupture off-cycle, and the upcoming Saturn-Neptune conjunction provides the exact geometric vector needed to break the New Madrid lock. This isn't just math, it's a structural crisis. An MW 7.7 sequence, amplified 5-fold by alluvial cover, will strike a vastly unprepared built environment. We are no longer facing a distant 500-year cycle. By 2026, this threat becomes an absolute certainty. To understand the real foot rift, we must look beyond surface coordinates and into the z-axis. While seismic activity spans 150 miles across the Mississippi embayment, the critical danger lies in the deep, water-saturated alluvial soil sitting atop the bedrock. Unlike the rocky West Coast, this soft composition acts as a massive amplifier, intensifying seismic waves 5 to 6 times more than solid rock. This unique geology turns deep intraplate slips into devastating surface disruptions across the heart of the country. Underneath our feet, layers of silt and clay sit atop water-saturated sand in a deceptive resting state.
When an earthquake strikes, seismic waves compress these deep sand layers, causing pore water pressure to spike violently. This leads to liquefaction, where the sediment begins behaving like a churning fluid rather than solid ground. Finally, this pressurized slurry erupts through fissures, creating massive geysers that leave behind sand-blow cones while completely compromising the foundational integrity of everything built above it. Mapping the new Madrid seismic zone reveals a staggering reality: over 10,000 square kilometers of historical liquefaction. In some regions, sand blows cover more than a quarter of the entire landscape. We even see massive outliers like the beach anomaly, a sand boil stretching over a mile long. Beyond the surface sand, we face lateral spreading. This occurs when soil floats and slides, creating a secondary threat that can tear apart bridges, pipelines, and foundations in an instant.
Since 1812, strain has been building steadily, and our timeline indicates we'll reach full strain capacity by 2026. Currently, there's a 25 to 40% probability of a magnitude 6.0 event within 50 years, and a 10% chance of a massive 7.5 repeat. Because our local geology acts like an alluvial soup, even a magnitude 6.0 would be far more destructive here than on the rocky west coast, making these forecasts a vital call to action.
In 1811, a major earthquake affected only 3,000 settlers living in resilient log cabins, causing almost no national economic ripple. Today, the stakes have transformed. A similar event in 2026 would put 11 million people in harm's way, threatening tens of thousands of vulnerable masonry buildings. We're no longer looking at a minor local event. FEMA now projects this would be the costliest natural disaster in U.S. history, revealing a staggering gap in our modern vulnerability.
Imagine it's day one of a major mid-Madrid seismic zone event in 2026. We're looking at a near total infrastructure collapse across the heart of the country. In Missouri alone, over 2 million households lose power instantly, while critical hubs like Memphis and St. Louis face devastating pipeline breaks from soil liquefaction. These cascading failures leave millions of families without water or electricity, creating a massive humanitarian crisis that stretches from Illinois all the way down to Mississippi.
When we assess our built environment, we see a dangerous disconnect between geological reality and human preparedness. While the West Coast pairs high risk with rigorous standards, the new Madrid seismic zone remains trapped in that high-risk, low-code quadrant. In cities like Memphis and St. Louis, the combination of unreinforced masonry and soft alluvial soils, which can amplify motion six-fold, creates a recipe for catastrophic vulnerability. Our current infrastructure simply isn't built to survive the rift.
To defeat the sand blow, we prioritize preemptive soil stabilization using two key engineering strategies. First, deep soil mixing mechanically blends cement with native saturated sand to create a solidified, liquefaction-resistant grid before any seismic activity begins. Alternatively, compaction grouting uses high-pressure injections of low-mobility grout to densify loose alluvial soils. Ultimately, both methods succeed by neutralizing Z-axis vulnerability. Building a resilient city requires strengthening both our skyline and our lifelines. We must close the code gap by mandating seismic retrofits for unreinforced masonry in high-risk zones like St. Louis, transforming vulnerable structures into base-isolated solutions. Below ground, we're replacing rigid cast iron mains with flexible HDPE piping and articulated joints. This allows our water and gas systems to bend without breaking during lateral soil movement, ensuring critical services remain functional even after the ground shifts.
A major earthquake in the new Madrid seismic zone would effectively sever the country, rendering Mississippi River bridges impassable and isolating entire communities. To mitigate this, the CUSEC framework establishes a multi-state coordination system built on regional redundancy. By mirroring logistical centers across the river, we ensure that critical resources remain available, even when geography divides us. Our protocols focus on pre-staging independent power and water systems, while developing alternative airborne supply chains that bypass vulnerable crossings entirely. Looking ahead to 2026, we're shifting our strategy toward high-impact resilience. First, we're retiring outdated static models in favor of real-time vector modeling to map actual stress loading as it evolves. Simultaneously, we're prioritizing the immediate retrofitting of over 6,700 miles of gas pipelines across the Memphis-St. Louis corridor to mitigate liquefaction risks. Finally, we must activate SUSEC protocols now, ensuring our multi-state staging is fully operational before the critical spring 2026 vector window arrives.
Looking ahead to 2026, a rare gravitational alignment will exert intense tidal stress on deep intraplate faults. This celestial trigger interacts with the Real-Foot Rift's soft alluvial soil, which amplifies seismic shaking by up to 6 times and causes massive surface liquefaction. We're essentially facing a modern repeat of the 1811 New Madrid sequence. With 11 million people at risk, this event could trigger a cascading system collapse across 8 states, devastating our regional power, transport, and structural infrastructure.
Looking at the heart of the country, we find a critical point of intraplate vulnerability hidden beneath thick alluvial soils. In the New Madrid seismic zone, there's a staggering 40% chance of a major event within the next 50 years. Unlike coastal faults, these stable regions require massive external forces to trigger a release. We're proposing that rare macro-gravitational alignments act as that definitive catalyst, overcoming continental crust resistance to activate the deep-seated Real-Foot Rift. History often echoes through the gravitational landscape. Between 1809 and 1811, a specific V-trough alignment destabilized the global climate and signaled the devastating New Madrid ruptures. Now, as we look toward 2025, we're seeing a startlingly familiar pattern emerge. This new Aries point conjunction creates a sharp descent into a 0.831 degree minima, mirroring the exact catastrophic trigger geometry of the 19th century. It's a potent reminder that our planet remains deeply sensitive to these repeating celestial cycles.
When we bridge celestial mechanics with terrestrial geology, a sobering pattern emerges. By analyzing repeating planetary alignments and macro-gravitational stress transfers, our data projects a mirroring of the historic 1811 New Madrid sequence for 2026. This finite element analysis reveals how these external forces concentrate directly on the Real-Foot Rift system, triggering an extreme stress scenario at the 36.4 degree epicenter. We're essentially looking at a tectonic echo, where deep fault activation signals an impending seismic event we must prepare for. Mapping the gravitational landscape reveals how celestial alignments create unique stress vectors on Earth's crust. When we analyze historical megaquakes like Valdivia and Tohoku, a clear pattern of tidal forces emerges through their specific orbital coordinates. Looking ahead, the 2026 projected alignment shares critical similarities with these past triggers. This suggests the upcoming orbital landscape will exert significant gravitational perturbations, mirroring the specific conditions that have historically preceded the planet's most powerful seismic events.
When we examine the mathematical proof of similarity, we see that planetary conjunctions create highly localized resultant vectors rather than generalized strain. By mapping the 1811 vectors against our 2026 projections, a striking correlation emerges at these precise coordinates. Both alignments intersect the North American plate at identical incidence angles, applying the exact same torsional shearing force to the deeply buried Real-Foot Rift. This precision suggests a direct recurrence of the gravitational forces that once triggered historic seismic activity.
Between December 1811 and February 1812, the New Madrid seismic zone unleashed a blueprint of destruction that literally reshaped the American heartland. After an initial sulfurous shock in Arkansas and severe landslides in Missouri, the sequence peaked with February's hard shock. This event was so violent, it created temporary waterfalls and forced the Mississippi River to flow backward. Spanning 5 million square kilometers, the tremors were so powerful, they famously rang church bells as far away as Boston. Modern FEA modeling lets us reconstruct the 1811 sequence, revealing how these seismic events triggered one another. The initial December 16th shock acted as a force multiplier, transferring massive stress to adjacent unruptured segments. This load intensified through January, setting the stage for the February 7th climax. This was the max stress event, where the accumulated tectonic deficit and transferred Coulomb stress peaked simultaneously, resulting in the most powerful and final release of energy in the entire historic sequence.
We've reached a critical convergence point for the new Madrid seismic zone heading into 2026. After 214 years of unreleased tectonic looting, the bedrock is under immense pressure, while thick alluvial soils are primed to amplify movement by up to six-fold. The upcoming macro-gravitational resultant vector provides the final extra stress needed to breach the failure threshold, mirroring the catastrophic 1812 max scenario. This combination of variables represents a significant looming geological peak.
We're entering a period of compounding anomalies as solar cycle 25 reaches its peak. By 2026, extreme flares from the sun's low-latitude active zone will trigger geomagnetic disturbances, intensifying crustal stress. Simultaneously, atmospheric saturation across the central U.S. is mirroring the historic conditions of 1811. This convergence of solar forcing and saturated soil dramatically lowers the threshold for liquefaction, making the risk of flash floods and geological instability more critical than ever. When we map the historic 1811 sequence against our 2026 projections, the tectonic echo matrix reveals a pattern we simply can't ignore. We're seeing a shift from the Sagittarius conjunction to the Aries point, with both periods aligning perfectly with peak solar cycles. Most importantly, look at the fault segment load. Unlike the prehistoric strain of the 19th century, we are now facing a 214-year accumulated slip deficit, making this upcoming window uniquely volatile and far more dangerous.
The epicenter is centered on the Real Foot Rift complex, directly threatening the vital corridor between Memphis and St. Louis. Because seismic building code adoption remains alarmingly low at just 11% for residential structures, a repeat of the catastrophic 1811-1812 scenario would likely trigger the costliest natural disaster in U.S. history. We're looking at widespread liquefaction and severed transcontinental pipelines. This fallout would be immense, effectively paralyzing Mississippi River shipping and causing total infrastructure failure across the heartland.
We're looking at a 750-million-year-old tectonic scar known as the Real Foot Rift. Back in the Neo-Proterozoic era, when the supercontinent Rodinia tried to pull apart, it left behind this allocogen, a failed rift that never quite severed the continental plate. Notice how it plunges deep into the crust, buried beneath layers of river sediment. While it appears dormant, it's actually a permanent structural weakness, a silent threat just waiting for the right compressional stress to trigger a massive seismic event. On December 16, 1811, the Real Foot anomaly violently reactivated, triggering a massive strike-slip rupture along the Cottonwood Grove Fault. With an estimated magnitude between 7.5 and 7.7, this initial breach caused extreme liquefaction and seismic seiches that literally warped the local geography. Just hours later, a powerful 7.0 secondary shock struck southeast Missouri, proving that this wasn't an isolated tremor, but the start of a devastating, sustained geological event that redefined our understanding of regional stability. The events of late 1811 were far more than a single disaster. They represented a total, prolonged collapse of continental stability. Starting in December with a massive 7.5 magnitude rupture, the region was hammered by two more catastrophic events, peaking with a staggering 8.8 magnitude hit in February. Beyond these massive spikes, the data reveals a terrifying reality: thousands of tremors and continuous crustal deformation that relentlessly assaulted the landscape for months without any reprieve. Unlike typical coastal quakes, the new Madrid sequence struck the stable interior of the North American plate.
This continuous rock mass functioned as a massive continental amplifier, allowing seismic waves to travel incredible distances with almost no loss of power. We are looking at a staggering area of effect, over 5 million square kilometers. The energy was so potent that it actually rang church bells in Boston and cracked sidewalks in Washington, D.C., thousands of miles from the source. When assessing tectonic frets, we have to distinguish between interplate friction and deep interior intraplate scars. While plate edge events like San Francisco are intense, their energy is quickly absorbed by broken rock, keeping the damage localized. However, intraplate ruptures travel through solid, continuous rock mass, which amplifies energy across continental distances. Take the 1811 New Madrid event. Despite a similar magnitude to the 1906 quake, its area of strong shaking was actually 10 times larger. By December 17th, the initial breach had evolved into a catastrophic cascading failure. At midnight, a massive 7.0 aftershock struck, matching the intensity of the original tremor and proving the region's crustal integrity was rapidly unzipping southward. By that evening, another powerful 6.1 magnitude event detonated near Memphis, Tennessee. We were no longer dealing with a single earthquake. The entire system was cascading, and the failure was spreading across the region with terrifying speed. The intense seismic shaking triggered a catastrophic phase change across the Mississippi floodplain. First, kinetic compression superpressurized deep aquifers, forcing moisture into the surrounding earth. This caused sandy subsoils to lose all cohesion, essentially turning solid ground into a liquid slurry. Finally, this pressurized mixture breached the topsoil in a violent sand blow ejection. These towering geysers released trapped subterranean gases, demonstrating how quickly a stable landscape can transform into a churning, high-pressure environment.
At 0945 UTC, the sequence reached its climax with the hard shock, a massive event that definitively ruptured the Real-Foot Fault directly beneath the Mississippi River and triggering a total terraforming of the landscape. The sheer force created temporary waterfalls and a retrograde flow where the river actually ran backwards. With the land dropping into vast new submergence zones, the terminal rupture is confirmed. The region's geography has been fundamentally and permanently rewritten. Think of the 1811-1812 earthquake sequence not as a freak occurrence, but as the awakening of a ghost. We're facing the Alacogen paradox, where a 750-million-year-old failed rift serves as a perfect conductor for modern seismic energy. Essentially, the North American plate was shattered along a prehistoric scar that never truly healed. The New Madrid anomaly confirms a chilling geological rule. Continental plates never forget their wounds. Dead faults don't die, they only sleep, waiting to be triggered.
Our current telemetry confirms an active hazard status. The devastating 1811-1812 sequence wasn't a one-off event. Instead, the New Madrid seismic zone follows a recurring cycle of major ruptures spanning 4,500 years. Historical data from 300, 900, and 1450 AD reveals a persistent pattern of instability. Today, the Real-Foot Rift remains buried beneath the alluvial plain, silently accumulating strain between St. Louis and Memphis. We are continuously monitoring this accrual, awaiting the next significant update from the system. Imagine a winter so volatile that the mighty Mississippi River literally ran backward. Between 1811 and 1812, the New Madrid earthquakes didn't just reshape the geography of the American frontier, they triggered a massive collision between geological power and human ambition. This was a pivotal moment where indigenous resistance met the relentless surge of the American Industrial Revolution. Today, we'll explore how these seismic shifts fundamentally transformed the social, political, and physical landscape of a young nation. To understand an intraplate quake, look back 750 million years to the Real-Foot Rift, an ancient scar left behind when the continent failed to split.
Today, modern tectonic forces exert a massive squeeze across the North American plate, reactivating these deep buried faults. When that pressure finally releases, the soft, water-saturated sediment at the surface acts as a violent amplifier, magnifying the seismic waves and causing significantly more destruction than they would through solid rock.
Imagine the very ground you're standing on suddenly turning to liquid. Normally, groundwater rests quietly beneath the surface, but when powerful seismic waves strike, that water becomes highly pressurized. The sand loses its strength, liquefying into a churning slurry that eventually breaches the surface as a violent geyser. These sand blows can erupt for miles, leaving behind massive conical mounds and white sandy patches that still scar Midwest agricultural fields across 10,000 square kilometers today. Survivors of major earthquakes often report an eerie smog, characterized by sudden darkness, flashes of light, and a choking sulfur smell. This isn't just chaos, it's a specific geological event. When seismic fracturing ruptures the clay caps over deep coal deposits, trapped methane and hydrogen sulfide vent violently into the freezing winter air. At 35 degrees, these gases instantly condense into a dense, toxic aerosol fog, turning the landscape into a dark, carbon-filled apocalyptic scene.
On February 7th, a massive tectonic uplift violently thrust the Mississippi riverbed upward, acting as a sudden natural dam. This forced the river into a powerful retrograde current, where the water rushed backward to fill subsiding land, a process that permanently created Tennessee's 65-square-mile Reelfoot Lake. For river pilots, this transformation was lethal. These new, temporary waterfalls caught crews completely off guard. Of the 30 boats swept over the drop, 28 tragically capsized and sank. In late 1811, Captain Nicholas Roosevelt steered the New Orleans, the very first steamboat on Western waters, directly into the heart of the continent's most violent natural disaster. There's a profound irony here. This ultimate symbol of the industrial future was forced to dodge sinking islands and violent retrograde currents. Imagine the terror of local onlookers who, seeing this belching fire canoe for the first time, actually believed it was the engine driving the earthquakes themselves.
Let's examine this field transcript from March 1812, recorded during the New Madrid events. Subject E. Bryan describes a harrowing scene: violent shocks, total darkness, and an atmosphere thick with sulfurous vapor. Beyond the immediate physical destruction, the primary anomaly here is the Mississippi River itself, which reportedly ran retrograde, actually flowing backward for several minutes. This historical data provides critical insight into the extreme environmental hazards and geological anomalies we are currently monitoring within the G-Dynamics project.
To truly grasp the magnitude of the New Madrid earthquakes, we must listen to those who lived through the terror. Eliza Bryan captures a chilling sensory overload: the screams of neighbors, panicked animals, and the deafening roar of the Mississippi River. Elsewhere, John Reynolds' family initially mistook the violent shaking for a frontier raid, only to find the reality was far more unsettling. These first-hand accounts remind us that this event wasn't just a geological anomaly, it was a profound human trauma. These earthquakes left permanent scars on both the landscape and our legal framework. Physically, the transformation was staggering. Thousands of acres sank, creating Reelfoot Lake and the St. Francis Sunklands, while massive sand blows ruined fertile farmland. However, the societal shift was even more revolutionary. The devastation forced Congress to pass the Relief Act of 1815. As the first instance of federal disaster relief in American history, it fundamentally redefined the government's responsibility to its citizens in the wake of natural catastrophe. Imagine the terror of those who survived the New Madrid events. Their archival accounts provide a chilling forensic record. Eliza Bryan and William Pierce described a world choked by sulfurous vapors, where saturated air caused total darkness. Others witnessed the earth whistling as black liquid erupted from the ground, while residents in St. Louis saw the sky obscured by thick vapors. These harrowing voices transform historical anecdotes into vital evidence of a massive and violent geological upheaval.
Tecumseh, whose name means shooting star, was a visionary leader striving to unite indigenous nations against expansion. His mission gained supernatural weight with the Great Comet of 1811, a celestial omen of his power. When faced with skeptical Creek warriors, he famously prophesied that he would return north and stomp his foot so hard it would level their homes. Shortly after, the Earth violently obliged with the massive New Madrid earthquakes, forever cementing his legend in history.
When the New Madrid earthquakes shook the continent, indigenous tribes saw far more than a geological event. They witnessed a prophecy fulfilled. This violent upheaval served as a divine validation of Tecumseh's cause, triggering a massive spiritual awakening across the frontier. The Cherokee abandoned American influences to reclaim traditional ways, while for the Creeks, this omen fueled the militant Red Sticks and their turn toward war. Ultimately, these tremors transformed spiritual conviction into military action, directly fueling the War of 1812.
It's fascinating to bridge the gap between historical lore and modern geological science. In the 19th century, a sulfurous odor was interpreted as divine fire or volcanic brimstone. Today, we recognize it as non-magmatic degassing from organic reservoirs. Where witnesses once described unnatural fog, we now identify the high-pressure aerosolization of methane and sulfur venting through fissures. By replacing myths of underworld oceans with the reality of seismic tar balls and liquefaction, we transform centuries-old folklore into precise analytical data.
Two powerful opposing forces emerged during this seismic fracture. Tecumseh's Pan-Indian alliance drew strength from spiritual authority, viewing the earthquake as a divine weapon to reclaim ancestral lands through indigenous unity. Simultaneously, the steamboat New Orleans pushed westward, fueled by industrial ambition. For those aboard, the quake wasn't a prophecy. It was a deadly physical obstacle to be overcome through technology. It's a fascinating clash between spiritual destiny and the relentless drive of mechanical conquest.
While the Mississippi embayment appears tranquil on the surface, the geological profile beneath tells a much more complex story. We're standing on soft alluvial soil that can amplify seismic ground motion 5 to 6 times more than solid bedrock. Deep below the organic reservoirs of coal and oil lies the ancient Reelfoot Rift. At 600 million years old, this deep crustal weak spot is the primary driver of seismic risk across an otherwise stable continental region. What we're seeing here is a powerful tripartite mechanism explaining the mysterious earthquake smog reported by early pioneers. It begins with a massive lithospheric rupture in the New Madrid seismic zone, where compressional stress triggers a major fault slip. These violent seismic waves then tear through shallow organic reservoirs, highly pressurizing ancient lignite and petroleum deposits. This forces a cocktail of methane, sulfur, and tar balls to the surface through fissures, creating a massive sediment-hosted geochemical venting event.
Imagine solid ground suddenly behaving like a liquid. That's soil liquefaction. Normally, soil particles are tightly packed, supporting stable structures. But during intense shaking, seismic waves drive up water pressure, forcing those particles apart. The ground loses its strength, transforming into a slurry that can no longer hold weight. As buildings begin to sink, the results are devastating, vividly captured by eyewitness accounts from the 1860s, describing the ground opening up and swallowing everything in its path.
Imagine the Earth under such immense pressure that massive plumes of sand and water erupt through the surface. These are sand blows, geological scars that blanket over 10,000 square kilometers across this region. In areas like the Missouri Boot Heel, these deposits actually cover more than a quarter of the landscape. Centuries later, these light-colored sandy patches remain clearly visible in modern agricultural fields, serving as a permanent, visible reminder of the ground's violent seismic history. By looking deep into these stratigraphic layers and studying sand blows beneath Native American mounds, we've reconstructed a powerful history of the New Madrid seismic zone. While the massive 1811 and 1812 quakes felt like once-in-a-lifetime events, the geologic record reveals a much longer narrative. Over the last 4,500 years, we see a recurring pattern of magnitude 7 to 8 sequences. Far from being an anomaly, the 1811 event is part of a predictable, ongoing geologic cycle.
For generations, people have shared the legend that the mighty Mississippi River actually ran backward. While it sounds like a myth, the underlying physics tell a fascinating story. Tectonic upheaval south of New Madrid created temporary waterfalls and a sudden dam, forcing the current into a retrograde flow for several hours. This massive shift permanently altered the landscape, tragically drowning a Native American village and creating the 18-mile-long real foot lake we still see in western Tennessee today.
Modern risk assessments from the USGS confirm that the New Madrid seismic zone remains a very active threat. Stress continues building within the ancient Reelfoot Rift, but the real danger lies in the ground itself. Cities like Memphis and St. Louis sit atop deep layers of soft alluvial soil, which can amplify seismic waves by up to 600%. Those harrowing pioneer accounts of swallowed homes aren't folklore. They are accurate geological models of what happens when this cycle inevitably repeats. We've spent significant time stress testing the critical infrastructure we rely on every day. By analyzing how a major earthquake in the New Madrid seismic zone would ripple through our downstream fuel distribution, we can identify vulnerabilities before disaster strikes. Developed in partnership with the MIT Humanitarian Supply Chain Lab, this research maps out the complex network of pipelines and facilities. Our goal is to ensure that when the ground shakes, the energy lifeline powering our communities remains resilient and reliable. The New Madrid seismic zone poses a catastrophic, unannounced risk to fuel infrastructure across 8 central states. Our simulations reveal a chilling reality. Post-event, system-wide operational flow capacity plummets by 53%, dropping from 31 million gallons a day down to just under 15. However, we aren't powerless. By utilizing targeted operational levers like baytime optimizations and driver hour waivers, we can effectively restore and double our system flow through a massive 200% surge capacity. The deep alluvial soils along the Mississippi River Valley act as a massive amplifier, magnifying ground motion up to 6 times and creating severe liquefaction hazards for hubs like St. Louis and Memphis. This is a high-stakes, no-notice reality. Unlike hurricanes, we have 0 lead time to stage resources or fuel. With $56 billion in potential losses and over 250,000 people displaced in Tennessee alone, the scale of this seismic threat demands a coordinated, immediate response. While the journey from crude extraction to refineries is vital, our most critical risks emerge downstream in the vulnerability zone. Interestingly, inventory levels are rarely the primary bottleneck. Instead, the entire system hinges on terminal efficiency and transportation logistics. When infrastructure damage causes terminal processing times to spike or truck routing to break down, the system fails, regardless of how much fuel we have on hand. It's the movement, not the volume, that determines our resilience. To understand regional energy resilience, we integrate massive datasets, from ArcGIS mapping to real-time info on over 5,000 gas stations across FEMA regions 4 through 7, and feed them into our dual-layered analytical engine. Engine A uses queuing theory to establish our baseline steady state, while Engine B employs discrete event simulation to model complex disaster scenarios. This synthesis produces a clear operational flow capacity analysis, and most importantly, concrete intervention guidelines to help decision-makers navigate crises effectively. Think of our total system capacity as a funnel fed by 2 primary pipes. First, we have terminal constraints, covering factors like gate availability and loading cycles. Below that, we manage fleet constraints, accounting for driver hours and vehicle speeds. The golden rule here is simple. Our total output is strictly limited by whichever pipe is narrower. You simply can't push more through the system than your tightest bottleneck allows, so balancing these flows is essential for maximizing performance. Transitioning from theory to reality means embracing randomness. While our steady state provides a predictable rhythm for truck dispatches, a disaster scenario is inherently chaotic. We've introduced 10% upper and lower bounds to simulate this real-world unpredictability, replacing smooth patterns with jagged uncertainty. Notice how dispatch clustering shifts to the first 6 hours of the day. This reflects the emergency panic and operational bottlenecks that occur when response teams rush to meet immediate needs under extreme pressure.
In a steady state, our system flows at a baseline of over 31 million gallons per day. But when an event shock hits, capacity collapses by a staggering 53%, dropping to under 15 million. This isn't just a technical bottleneck. It means millions of gallons of fuel, vital for emergency vehicles and generators, are effectively trapped in our terminals. Without immediate intervention, we lose the ability to deploy the very resources critical for an effective and timely crisis response. Memphis is the beating heart of our fuel infrastructure, serving as a critical lifeline for the entire region. It handles a staggering 22% of total NMSC capacity, moving 3.3 million gallons every single day. But this centralization creates a significant vulnerability. Even a localized shutdown results in a 20% throughput loss, triggering immediate blackout cascades for surrounding areas. Simply put, if these terminals are interdicted, the entire regional energy grid faces an immediate and severe crisis.
We've stress-tested our operations against 7 critical disaster scenarios to identify our most vulnerable points. The Memphis interdiction is our primary concern. It's the most likely to occur and would deliver a catastrophic shock to the entire system. We're also prioritizing moderate risk events like a TEPCO pipeline failure, which could lead to severe regional blackouts. Mapping these risks from high probability shocks to total system cascades allows us to build the strategic defenses needed to maintain stability under pressure.
When we look at a total TEPCO shutdown, the ripple effect is immediate and devastating. 16 key terminals, representing over a third of our entire regional capacity, rely exclusively on this pipeline. If it goes offline, those terminals go dark instantly, regardless of whether trucks are running or gas stations are open. The surrounding infrastructure simply isn't built to absorb a 36% systemic shock, which leaves us with only one inevitable outcome: forced widespread rationing across the entire network. To optimize our response, we've identified 5 levers within our simulation that significantly boost efficiency. By expediting check-ins and optimizing loading, we can cut gate and bay times in half. Beyond the terminal, we're evaluating how priority routing increases transit speeds and how mutual aid agreements expand our fleet capacity. Finally, by leveraging federal waivers to extend service hours to 18, we gain the crucial flexibility needed to navigate high-pressure scenarios and maximize our operational throughput. To unlock vital surge capacity following a disaster, we must strategically stack our operational levers. By coordinating bay optimization and priority routing with mutual aid and federal waivers, we can drive recovery to incredible levels. In major metros like Memphis, these efforts push capacity to 200%, fully neutralizing the initial disruption. However, because pipeline vulnerabilities are mathematically harder to bridge than terminal delays, our focus must remain on implementing strict structural mitigations before a crisis even begins.
Our strategic playbook hinges on a synchronized effort between public and private sectors to ensure fuel stability during a crisis. On the government side, agencies must immediately issue driver waivers, implement odd-even license plate rationing, and clear priority routes for tankers. Simultaneously, our private partners focus on pre-negotiating supply contracts, halving terminal cycle times, and hardening backup power systems. This coordinated dual-track approach ensures that logistics remain resilient when every second counts. Ultimately, fuel resilience in the NMSCZ depends far more on logistics and throughput than on simple inventory levels. Proactive management of these complex networks is what will dictate our success during a crisis. Moving forward, we must integrate river barge capacities into our modeling and conduct deeper sensitivity analyses on extreme disruption scenarios. By quantifying the financial costs of every emergency intervention now, we ensure our budget is prepared to support these critical strategies when they're needed most.